Okay, so now I'm going to try and describe this kind of local, global compatibility condition in initial theta data. So I just want to remind you kind of what was going on. So here this is so we had a tuple here. So we have M. So I think we either called it M or M underline, V underline, and epsilon underline. Okay, so these guys are okay. So there's L. So these are a tuple. This is going to be a tuple in initial theta data. Theta data, and so M. So again, we're going to fix an elliptic curve. This is an elliptic curve over a number field. This is a number field, and then what we did is we defined K. This is going to be the F adjoined the L torsion. It's F adjoined the L torsion of the elliptic curve. Okay, and it's also F bar and the kernel of rho L. L. This is the mod L Galois representation. So this is it in just the L torsion part. Okay, and here we defined so M. So this was this thing appearing in so we had M or so there was two curves. M, this was a subset of E underline L K, and here we had so I guess we just do K bar. M, this was contained in E L K. And then these things were, E mod M, so comma, EL mod M. But this is what we called E underline M underline. And this was this quotient is what induces the this comes from the Fricka evolution. Okay, and then we fixed, so these were the two things. So V underline, so this was a subset of V of the field of moduli. Sorry, this is it's a subset of VK. So this torsion field lifting V of Q of JE. I think we did J with parentheses. I'm probably going to switch between J subscript E and J parentheses E. So, and also, some of you guys just know, I might use this notation. Hopefully I don't. Okay, so we have this thing. This is a lift of these things, and then epsilon underline. So this is an element of M underline. Okay, and then it's really defined up to involution. And then L was, of course, L was a fixed prime. I've already used L, so hopefully it was clear what L was. Okay, so, and then for these, there was two sequences that come up. So there's two sequences. That we need to consider. There is this global sequence. It said that so we can ELK, and then we have this quotient, and we have this guy, this beginning thing. So we have this sequence here, and then we have a local sequence. So this is of So this is of GK modules. And then we had the local sequence, and this is for L, finite extension of QP, where EL, so this could be another elliptic curve, but let's say it's the same thing. So has a split. So like this could be a completion of let's say F, has split multiplicative reduction. Then we have EL L bar. This goes to some so a tall part here. Okay, and then okay, then we have this mu L here. So this is a sequence of sequence. So this is an exact sequence of GL modules. Okay, and so so what the local the conditions in initial theta data are going to require that these two things be compatible in a certain way. Okay, before actually stating this, I just kind of want to let's recall some things. So before explaining, so essentially, like, we're going to want the base change of this to be the other sequence. So the base change of the global sequence to be the local sequence. So before explaining, we need some things. So first of all, we need to describe the base change. And to do that, we need to describe, so we need a description of M bar in terms of covers. Covers. So in particular, we want this isogeny, the dual isogeny of the quotient, to be a cover. And then we'll briefly recall the description of the L torsion using the Tate uniformization. Okay, this was already done in a previous thing, but I just want to make it a little more explicit and then connect it to these representations. Okay, and so so let's talk about the two descriptions of okay, so sorry, let's say of not of M bar, but of let's say of covers associated to M underline. Okay, and let me say briefly that let's start. Let me just start. So the first one's via the Galois Correspondence. Okay, I'll just say what I was going to say. There's another video where we talk about how the torsion is related to the quotient of the fundamental group, okay, of an elliptic curve, okay. But so we use that. So what's the Galois Correspondence? So the Galois Correspondence says that subgroups, open subgroups of the fundamental group correspond to Galois covers, or correspond to covers. In quotients, so normal subgroups correspond to Galois covers. So the quotient okay, I'll state it in terms of K, but M underline. So this thing here gives defines a Galois cover here, E underline, or E underline. So this here with group naturally isomorphic to M underline. Well, how does this work out? So the idea is that we have so this uses, which is described in another video, that pi 1 ek, so mod L. So this is isomorphic to ELK as Galois modules. And so this means that we have we get a quotient, right? Here to M underline, and so this is this quotient, Q quotient, and so this thing, any quotient induces this cover. Okay, the other way was the kind of this explicit way was via isogenies, and so we had that here. This thing, this is given by a kernel M, and so we have this. I guess I stated this already before here. ELK. I'm writing it. I guess. Let's write it additively, like so. Okay. So, and then the dual isogeny is the one that we have, and these two things are the same. Okay, so like I said, that we kind of consider this M thing as like an elliptic curve with level structure. Okay, so that's these are these covers. So I want to talk about how to pass this to tempered fundamental groups, and then I want to talk about okay. There's this part here. I'm going to come back to this in a second. So let me just say the description of L torsion. So split multiplicative reduction is equivalent to having a uniformization. So you can always go to a quadratic extension if you have multiplicative reduction to get split multiplicative reduction. So that's by taking like the square root of these C4 over C6 or something like that. So this is this constant gamma, and this is in the back of Silverman in this Tate uniformization chapter. Okay, and so the idea here is that let me just say here, I want you to recall that epsilon underline is in here. Okay, and so what we're gonna want to do. We want to define. So we want to define epsilon u v underline for v underline in here, a bad place. And so this means it lifts an element of this thing, v bad mod. And this was a distinguished collection of places of the field of moduli, where it had bad reduction. It had to be non-empty and not equal to 2. But it could say just be one place, right? And that's a good case to think about. Okay. So all right. So we have okay. So recall that. So E over L with split multiplicative reduction. So L is over QP, say a finite extension. And so this gives E an isomorphism here of L elliptic curves. Okay, so this is the Tate model here, and then the Tate model has a Tate uniformization. So so we will have so we use the notation phi of L cross Q to the L or Q to the Z. This thing will go to E. So I'm just going to write it as E. E is really isomorphic to EQ. Okay, so this is the Tate uniformization. Okay, and so this has some explicit functions that do that. Okay, and then so we already showed that and this is again that EL of L bar has a transvection basis. P1 and P2 in EL L bar such that so there exists some sigma in the inertia with you know, sigma of P1 is P1 and sigma of P2 is P1 plus P2. Okay, and so with respect to this basis, sigma, rho L sigma is this 1101 thing. Okay, and so this is the first basis. This is the first column. So this is the 1 0 column vector, and this is the 0 1 column vector. Okay, and so so the choices that are made here is that so we take Q to be equal to Q to the 1 over L, some root, and then zeta is, so this zeta is a Lth root of unity and sigma is an element of this. So this is how you can write down the torsion field over. So this is sigma's in L over L zeta like this. So this is the inertia part of this extension, and so we'll have that P1 is phi of Q. Let's see. P1 is phi of it's phi of zeta, and P2 is equal to phi of Q. And so sigma, so since we have a Kummer extension, sigma of Q is zeta Q. All right, so these are the choices that we have. And so so let's look at this. So we mentioned already that we have an extension. So we have this extension mu L bar. This goes to EL L bar. This goes to this goes to what am I talking about here? This goes to Z mod L. Okay, and then we'll write that one as a 0 and this one as a 1. And in terms of ramification, okay, and so let me write this. I guess we can write this out a little bit. So this thing here is isomorphic to zeta to the z. This is zeta z q to the z, mod q to the z, and this is zeta to the z q to the z mod zeta to the z, q to the z, like so. All right, 0, or we'll do 1s on this side. Okay, so we have this thing. Let's go up. So these are all via the Tate uniformization up. Okay. Okay, and so okay, so like, again, what are we going to do? We're going to look for this epsilon underline, which is going to be a generator here. Okay, so yeah, and so there's so the generator here. Let me just make remarks. The generator here is really q to the 1 over L, which is q, and this is a mod, the group generated by zeta and q. Okay, so that's what we have. And in terms of okay, I wanted to mention that this sequence here is canonical, meaning that so this sequence, so the sequence doesn't depend on the choices q or zeta. And I think that's all I want to say about that. And then let me just make like a little remark about the. So let me just make a little remark here about the. So we'll notice that there's how this ramification works, right? So here we have a kind of a sequence. So one. So we have a, okay, so we'll have a sequence here. So let's write down the inertia. So let's write down the inertia sequence. And this is, so here we're going to have G of L Q zeta over L zeta. So this thing, these guys will fix the zetas, so we'll have the sigma in here. And then we have G of L Q zeta over L. This is a Galois extension. So this is the torsion field extension here. And this goes to G of L zeta over L. And this goes to 1. So this is the unramified part. So this is the unramified extension, right? And then this part here is this is the ramified part. This corresponds to ramification, right? And so this is the unramified part, and this is the extension of the unramified part. Okay, so okay. So I just wanted to make another remark, was that that here, so it's like, how canonical is this sequence here? So let's look at this sequence. So how canonical is this thing? And how can we pick up this generator, right? So so I wanted to say the generator can be identified abstractly if we allow ourselves valuations. In particular, you know, we can take the valuation of this thing. You know, we can take the valuation of this thing, and we'll get you know, we'll be able to pick up that dude. Okay, so so let's talk about so relating M underline to its tempered friend to the local situation. Okay, so if so let V underline in here be a bad place. So bad non-Archimedean place. This means that it's it's sitting over one of the distinguished primes in the field of moduli, and so we'll note that here, there's a we have a pi 1. Okay, so there's a fact is that pi 1 temp of let's say, well, I don't know how abstractly we want to do this, so let's just do this. This is kind of a general thing, but I'll just stick with this particular situation. So E V underline here. So here, if we complete this, this is isomorphic to pi 1, the tall fundamental group of EV underline, or EV underline. Okay, so so there's a map. Okay, so also there's this one, and then EV underline here. So this is E, and then we're going to tensor up to KV underline. And so this thing has so this is really a fiber product, and it really has a natural projection EK to EK, like so. And hence these two things give a map from, okay, so this one, this one here, this induces a map from pi 1 tall of EV underline to pi 1 tall of EK. Okay, and this induces a map, so this induces a map from pi 1 of the tempered fundamental group to EV underline to pi 1 tall of EK. All right, so we have that now. And let's call this C. This is the completion map. Okay, so this is this completion map. Okay, so now this completion map allows us to pull back the quotient, this map FM underline. So this is here from pi 1 EK. So this is what we talked about in this description to M underline. Here, it allows us to pull this back. Okay, so if we call this map C, then we get a map here from group homomorphisms. Okay, from pi 1 here of so a tall of EK, and this goes to M underline to so I guess these are GK maps, and this is pi 1 G. Okay, so this is the local Galois group, pi 1 temp of EV underline. So then you give this like the Berkovich, you give this the structure of a Berkovich or a rigid space or something, and then you can talk about the tempered topology to M underline. Okay, and this is the pullback map, and it takes this FM to C star FM, which is FM composed with C. Okay, that's in here, FM underline. All right, and so this gives us a quotient, and then by the Galois correspondence again, so hence by the Galois correspondence, the Galois correspondence for tempered covers so we get a cover of we get some EV underline here, okay, to E underline, or sorry, to EV underline, and this has a Galois group M. Okay, so we get this Galois, we get the Galois cover at the finite level. All right, so that's how we pull things back. Okay, so now we can talk about compatibility, but first let me talk about pulling back the level structure. Some compatibility. So the pullback of the level structure. Okay, so what did we start with? So we started with so here's how this works. So we started with pi 1 temp. Okay, I'm just going to kind of omit because this is going to be on the same. So this is local. Well, okay. Maybe I'll write it once. Okay, and then okay. Let me just keep going. So pi 1 temp here E B underline mod L. Okay, and then we were given this thing. So this was C star FM underline. So this was this map that we were given. Okay, so so we had a YouTube thing on this. So there's this Hurevich map. Hurevich. Okay, this goes to this here, and so let's call this HV underline. Okay, so we have this description here, and so I have another video on this sort of thing. It's pretty important. So, okay, and once we have this, so this is an isomorphism, and I can define a map like so that defines alpha. Okay, so alpha allows us to define this thing, beta v underline, and we'll take this to be kernel. We'll take the kernel of this map alpha to be this map, and then here to be the inclusion coming from the construction of this limit, right? And this thing is going to be defined to be mv underline. Okay, once we have mv underline, what do we do? So, well, what we'll do is we'll take the co kernel of this map, beta v underline, and we'll define this to be the m underline v underline. Okay, so this is what we have for this one. Okay, and okay, so we have so now we have this the sequence, this exact sequence that was now pushed to the local situation. Okay, after we have that, we can go one further. So we can go down using, so I'll write it backwards, but we wrote the Tate uniformization going this way, but we'll take the inverse of this map, and we have the Tate uniformization here, modulo this Tate parameter. We can take the L torsion, and then we can define again this version here. So we can call this the Tate version of alpha, the localized version. What we'll do is we'll get this thing. We'll define the kernel Tate here, kernel of alpha v Tate, right? And and then after we have this kernel, we'll go one more, okay, and then we get to define the co-kernel of this map here, which is the uniformized version of essentially this thing here. Let's recall that here we have this description of this. So this was generated by zeta L to the Z, Q to the Z. So these were these two generators that we picked, modulo Q to the Z. Okay, so so this depends on this depends on choices of generators. Okay, but we have this kind of description now, and there's a so this thing is this thing has a kind of a canonical generator given by Q, so this kind of gives a comparison with the local global sequence, right? So I mean, this shows that from this global sequence, we can get a local sequence, and okay, so like we could ask, for example, does the theory of weights give us this canonical decomposition? There's some videos on this. Okay, so but what we want to happen is we want there's a canonical generator of this. So this has a canonical generator. Well, actually, this is well, yeah, up to. And what we ask is that so we'll have an isomorphism here. We'll ask that so the image, so this thing contains epsilon, right? And we ask, so we'll ask, so the condition is that, so the compatibility condition is that the map, okay, so we have, well, I guess we could extend this here. So that this is a, so let's see how we want to do this. So so this is a GK action. So let's say that K. So this so K is in here. So K sits inside K V underline, and then we can fix some algebraic closures. So we can put K bar inside K V underline. And so this gives G of V, the subset of GK. And then I guess we can ask that this map here, so the condition we want is we want this, so this is a sequence, this is a GV sequence, and then this is so this sequence is a GK sequence. And then there's this there's a map from here to here, and then we want I guess this induced map up to be an equivariant map of modules, and in particular we want this the compatibility requirement is that this generator here map to a canonical generator here up to plus or minus 1. So you define this thing up to plus or minus 1. Okay, so that's what we want to say about. So that's the compatibility condition between the local and global things. Is that every time we localize at one of these bad places, this thing gets mapped to this thing.